So we now have the building blocks that determine how Earth's climate is controlled. But there's one more piece to this that you need to understand as we think about Earth's climate, and that is the idea of feedbacks. So a feedback is essentially a loop of cause and effect, and there's two basic types of feedbacks. They're positive and negative feedbacks. Positive feedbacks are amplifiers, and negative feedbacks are stabilizers. And the way to understand this is to imagine bowling in different kinds of bowling alleys. So if you went to a fiendish, horrible, wicked bowling alley that had sort of a mound in the middle of the lane, so you're standing here and you're trying to roll the ball down the center here. If you're off by a little bit, say in a positive direction here, it's going to tend to pull the ball even farther in the positive direction. This is why it's called a positive feedback, because the response of the feedback is the same as the direction of that you're off. So if you have a little bit of a perturbation, it gets amplified by this positive feedback. A negative feedback would be like a nice sort of kiddie bowling lane where you've got sort of a gentle trough in the lane, and you got the gutters here. And if you roll it and you're off a little bit here, say in a positive direction, the feedback is going to go in the opposite direction. It's going to tend to push it back in the negative direction. That's why this is called a negative feedback. And this tends to stabilize the bowling ball in the center of the lane here, so it makes it easier to roll. So it's important to realize that if the positive feedback, if you roll the ball on the negative side of the lane, it'll tend to go also more negative. So positive feedback doesn't always make the Earth warmer because warmer is a positive number. A positive feedback could make the Earth get even colder if you did something that made the Earth cold. A positive feedback in general is an amplifier. We've seen a couple of feedbacks already in this class. The kitchen sink analogy is a classic example of a negative feedback. So the analogy again is that you have water flowing into the sink from a faucet, and it sort of builds up in the sink until it gets high enough that it can push water down the drain as quickly as it's coming in from the faucet. And this works out to be that there is a negative feedback on the water level in the sink. Because if the water level gets too high, the drain rate goes up and it tends to pull the water level back down again. Or if the water level is too low, like when you first start out and turn on the faucet, the drain rate will be too low and you'll tend to build up the water vapor concentration, or the water level in the sink. So if you were to start from a sink that had no water in it and turn on the faucet, the water level in the sink would relax to the equilibrium value. Or if you were to walk up to it and dump a bucket of water in, so you had too much to start with, it would relax back down to that equilibrium value. It's being stabilized by this negative feedback. There's also a negative feedback that we talked about controlling the temperature of the Earth, and that is due to the fact that infrared light leaving the Earth depends on the temperature of the Earth. The warmer the Earth is, the faster you're shedding energy out to space, according to epsilon sigma t to the fourth. And so in the same way, if you were to start out with an Earth at absolute zero and turn on the sun, the Earth would warm up until it reached an equilibrium temperature. Or if you were to crash a big meteorite into it and make it too hot, it would cool down and relax toward that equilibrium value. So those are both examples of negative feedbacks. One of the simplest positive feedbacks in the climate system is called the ice albedo feedback. Albedo is a word that it means the fraction of light that gets reflected back out to space. So when visible light comes in and gets reflected back to space, it doesn't deposit its energy as heat to the planet. We saw the albedo in the layer model. So the higher the albedo of the planet, the colder the planet is, because it doesn't use that energy, that light, to fuel its own thermal energy. It just loses it off the top. So the feedback with ice is that ice and snow are very reflective. So if you have a layer of snow over ground, it will cause the visible light to be reflected back out to space. It'll have a high albedo. And then you make it warmer, and the light then will hit the darker ground and be absorbed. So this will have a lower albedo. So if you absorb that light now, it makes the Earth warmer. So going from a cold state to a warm state tends to be amplified by the melting of the ice. And so in this sort of a feedback diagram, the state variable is the temperature, which gets fed back to. So a perturbation to the temperature that makes it a little bit warmer causes ice to melt, which makes it warm up even more. So this is an amplifier. This also works for sea ice, because sea ice is very reflective, and the ocean is some of the lowest albedo material on Earth. And so if you have sea ice, it's going to reflect the light back to space. You melt the sea ice, the light will be absorbed in the ocean. It's suddenly getting added to the Earth's heat budget. The water vapor feedback is a positive feedback that has an important impact on Earth's climate with rising CO2 concentrations. In fact, if it weren't for the water vapor feedback, there really wouldn't be as much of a global warming problem at all. The water vapor feedback something like doubles the sensitivity of the Earth to changes in greenhouse gas concentrations. At the heart of it, there's actually a negative feedback that controls the amount of water vapor in the atmosphere. So the state variable here is the water vapor. And if the water vapor concentration is perturbed by some external thing, like if you run a garden sprinkler, it changes the rate of evaporation someplace else, or else it just rains out someplace else because you put more water in the air. So the hydrological cycle leads to a negative feedback that stabilizes the amount of water vapor in the air. That's why running a garden sprinkler doesn't lead to global warming. But the vapor leads to a positive feedback operating on a state variable now of temperature. So the way this works is that if you have some perturbation to the temperature, say by making the sun brighter or adding more greenhouse gases, it changes how much water vapor you want to hold in equilibrium. It redefines 100% relative humidity, essentially. And so if you warm things up by some external means, that leads to an increase in the amount of vapor pressure in the air. And then water, as you know, is a greenhouse gas because it's got 3 atoms. You know it's a greenhouse gas, and it's asymmetrical. So having more water vapor pressure means that there's more greenhouse gas forcing to warm the Earth even further. So the way this could go is you add some greenhouse gas, or you make the sun warmer, and then that makes the temperature go up by itself, which causes the amount of water vapor in the air to go up, because the warmer air can hold more water vapor moving in this direction on that pressure curve. And then that's a greenhouse gas, so that causes the temperature to go up even more. It amplifies the temperature. So you may wonder, you have this loop of cause and effect. You may wonder, where does this end? Well, the answer can be seen on a diagram such as this one, which is a phase diagram for water. So it's got dimensions of temperature and pressure of water vapor here. And then it has these different regions on the graph. So up here, where the temperature is fairly high and there's a lot of water vapor, you can have liquid plus vapor. If you have a lot of water vapor pressure, but it's very cold, you're going to have vapor plus ice. Or if the vapor pressure is very low, then you may not have any other phase other than vapor. You'll only have vapor in this region of the phase diagram. So we're going to do sort of a thought experiment where we start out a planet and we'll say, let's not put any water vapor in the atmosphere yet. And we'll just have it be dry, and then we'll calculate what the temperature that planet would be. And so for Earth, that would lead us to a point sort of right here. But now, if it's got liquid water, it's going to evaporate. The liquid water is going to want to evaporate until it starts to be along this line here. So as the water vapor evaporates, it causes the temperature of the planet to rise because water vapor is a greenhouse gas. But ultimately, this trajectory hits the phase boundary to liquid, and at this point, it rains. And so the runaway greenhouse, the water vapor feedback is limited on Earth by intersecting the phase boundary for liquid water. The hydrological cycle is stabilizing, and it limits the extent of the water vapor feedback. If we back to this one, this is Mars. It starts out colder, and you add water vapor, and it goes up, and maybe it hits the phase boundary of ice plus vapor. So on Mars, it would snow. But again, the water vapor feedback would be limited by this phase boundary. Now, Venus is a different story. Venus originally had water. It doesn't anymore because Venus suffered a runaway greenhouse effect. If you start from a condition that's warmer and you raise the water vapor concentration and raise the temperature, it can curve over and miss the phase boundary for liquid or solid entirely, and this is called a runaway greenhouse effect. So all of the water on the planet would go into the atmosphere. It would all boil. And this is a one-way street. If this ever happens on a planet, it never can go back, because if you get too much water vapor up in the upper atmosphere where it's exposed to the ultraviolet light from the sun, this ultraviolet light can split the water molecule into hydrogens and oxygens. And these hydrogens are so small, they travel quickly with their allotted kinetic energy just put into that small mass. They go very fast, and so they can be lost to space. So a runaway greenhouse effect is the end of a biosphere for a planet. So looking at a picture of Earth from space is always astonishing to me because the atmosphere is so thin, and the ocean is just right there, spread out through the whole surface of the planet. And what keeps this from happening on Earth is sort of a cold trap. The fact that it gets so much colder in the upper atmosphere, the water vapor can't get through it. It all rains or snows out. So it's just like this very, very thin layer of cold air that has protected and guarded all of Earth's water for these billions of years. It looks so fragile to me, looking at a picture of Earth from space.